Okay, so this is some leftover from last time, lecture 10, where we were talking about nutrients. And I left you with this slide and asked if you just sort of think about it a little bit, which is that it's kind of a summary of all the processes that happen in a surficial environment, obviously a tree, and this is supposed to be soil and so forth. And there a through flow of water, right? And this is what feeds groundwater, to some extent feeds surface water, depending on the environment. And there's a whole bunch of processes that basically waylay chemicals on their way through this process. And to some extent, nutrients and things that are tied up in the ecosystem will spend a longer residence time in the environment than the water, and they'll cycle between various forms that are part of the living biomass, forms that are part of the leaf litter, parts that are sitting maybe on the surfaces of plants, for instance, that are dissolved into rain. And this can include components that are part of the biological entity itself, as well as things that have landed on it, like dust and so forth. And stuff gets washed through into the soils. We've already talked about last week all these processes that happen in soils. The weathering that takes primary material from the rock and adds it up into the soil column. But there's also all the sort of sorption processes and ion exchange processes, the addition of organic matter, and all of these things tie up with the nutrients, keep them basically in this part of the system so that they're available to be supplied to the plants. And things that happen that change characteristics of this process, whether we add stuff to the soil, like for instance, acid from acid rain, or maybe this is an agricultural soil, we pull the plants off and we sort of circumvent this process of readdition of organic matter. And you can imagine other things too, catastrophic events, a large flood or an erosion event or something like that. All of these things disrupt the kind of normal cycle and budget of nutrient elements or nutrient chemicals as they kind of naturally reside in the system. And you can also imagine all sorts of human ways in which things are degraded through addition of pollutants or stripping of materials off the soil or what other kinds of land use practices. And so there's a difference between a cultivated soil and a natural soil, especially between how well developed the layers are, how old and undisturbed it is, the fullness of the ecosystem. Many agricultural or cultivated soils tend to be monocultures with just one or a handful of organisms living on the land surface. So all these things play a role. And when we think about how the kind of nutrient elements that we've talked about are held or released, right, we see that phosphorus followed by nitrogen are the most strongly retained in this system for different reasons. Phosphate as an anion, nitrogen largely as a cation, and some of these other kind of essential elements that we talked about last time, less and less held progressively. So I also just kind of wanted to emphasize that microorganisms are super important in this process. They're important in the degradation of organic matter as one role of providing chemicals that were brought up into biomass. And we have leaf litter, and we have microorganisms breaking that back down and adding stuff back to the soil. That's a process. It's important. But another thing that microorganisms do is fix. That means make chemically reactive in a biological sense nitrogen from into the atmosphere, which isn't biologically active, to one of the forms it is. And that's summarized on another slide. There's also, this idea of regenerating decaying organic matter. And as we talked about last time, microorganisms can also play a significant role in the breakdown of inorganic materials in the soil, and that liberates new elements as well. So from the kind of perspective of providing nutrients to an ecosystem, there's sort of like three levels of material in reserve before we get to the root of a plant, right? There's the minerals that make up the matrix of the soil, whether we're down in the saprolite or up higher up. And we talked last time about there's different minerals in different parts of the soil column, depending on variations in pH and organic matter and maturation. There's also the active surfaces that those particles present, and they can have absorption on them. There's also organic matter that's been added largely from above, and it's primarily a store of nitrogen, phosphorus, and sulfur. There's some other chemicals in there too, but that material gets broken down in both cases, and there's different processes involved here. Microorganisms are involved in both, and these liberate chemicals in the soil solution, which can then go up into plant roots. And so, again, when you think about like an agricultural soil, in essence, what we're doing is kind of circumventing the process in the rate, the natural rate at which this happens. We're just adding a bunch of extra fertilizer so that we can have a biomass over here that's something like 10 times, 50 times, whatever the number is for that particular setting, natural. And there's really no way to crank up the rate of these processes. Or even if you could, you would sort of, it'd be like going into your savings account, depleting the resources that are meant to be there long term for something short term. And this is something that, you know, whether it's human enhanced or it's a natural process, this is something that kind of limits the amount of biological productivity in a terrestrial ecosystem. It's the rate at which stuff can be transferred from the long-term stores into bioavailable forms. And this is just kind of a graphic showing you some of the processes involved in what I just talked about, with a little bit more detail about, you know, what are some of the things that move things in either direction between the kind of long-term storage in soils, in the inorganic minerals and organic chemicals, and the living organisms. And they kind of, you know, pass through either in these mobile water-soluble forms or organic detritus that's sitting there shallow and relatively labile and reactive. And I'm not going to go through each one of these processes. Most of these I think you'll recognize. You may see some that are familiar, but you can think through them. Like, for instance, erosion. What's the role of erosion, and how does that perhaps redistribute materials between these various reservoirs? But they're important. And this is a diagram showing you how microorganisms transform nitrogen. You don't have to memorize any of the names of any of these things, but most of the nitrogen on the planet is in this form of N2, which we breathe in and out all day. We don't transform it. It's not biologically reactive, but nitrogen is one of these critical nutrients. And so there are some organisms that can take this nitrogen and make it into forms that other organisms can use. The forms that they like the most are sort of nitrate and nitrite. Those are very common forms that bacteria can transform nitrogen, whether it's through the breakdown of organic matter or whether it's directly of N2 that's sitting in the pockets in you know, the pore spaces in soils. There are also some organisms that can make NH3 or NH4 plus. Now, on top of all that, there are organisms that can transform between these forms, as well as organisms that can take these forms and convert them back into nitrogen. And so there's a whole kind of consortia of organisms and processes that go on that transform some small fraction of the total nitrogen into these bioavailable forms. And they're, again, part of a healthy ecosystem, and they're necessary. Some plants have the ability to do this themselves. There's very few of them. Many of them can do it through the association of microorganisms with their roots, either on the outside of the root or even sometimes interior to the root. And I just want you to be aware that these processes happen, and in fact, they're essential, right? That we wouldn't have the biological productivity on the planet through photosynthesis if we didn't have organisms that were able to affect these redox transformations. And hopefully you can see this is just to go between N2 and all these various other forms of nitrogen. This is redox, exchange of electrons. And so these are just some kinds of organisms that do what we call nitrogen fixing. And I only point this out again, don't have to memorize any of the names of anything. These are things you can always look up, but there's basically two mechanisms that organisms use. One is as a kind of a standalone organisms that are living in the soil. They're just doing their thing that plants are taking advantage of. Those are the non-symbionts. And then symbiotic relationships are ones where the microorganisms are like part of the root or on the root and very closely associated with, with the particular plants. Symbiont implies there's something going back and forth. So the bacteria that are doing the nitrogen fixing, for instance, in these soybean roots, and these are something called rhizobium bacteria, they live in and on these nodules, and they're getting something as well as the plant getting something. So they're giving the fixed nitrogen to the plant, and what they're getting in return is carbohydrate, fixed carbon that they can use as their energy source. And that's just a strategy that happens to work in this particular case. It's much less common, but we do find it occasionally that the same thing can happen for phosphorus. Phosphorus tends to not be limiting in most soils because it's so water insoluble. There's usually more phosphorus available than nitrogen in many terrestrial soils. But we do find plants that can, again, through the structure called the Hydrosphere mycorrhiza, which are these kinds of things, there are fungi that can take in phosphorus in a way that can be transformed and make it bioavailable to plants through their roots. And so this happens for phosphorus as well. And the only reason I put those last little slides in there from last time was to just kind of help illustrate for you the importance of both microorganisms and interconnections, both chemically and biologically, in terrestrial ecosystems. So this week, we are going to talk about more hydrosphere. We've already talked a little bit about the hydrosphere and the hydrologic cycle, but now we're really going to think about the things that affect the chemistry of it. And so we'll talk a little bit about, some of the stuff will be reviewed from what we talked about during the first week. So I'm going to go through some slides kind of quickly, but just to kind of remind you of stuff. The reservoirs and fluxes of the hydrosphere, some important properties of water, both chemically and physically. And then we'll talk about some internal motions and stratifications, then getting on to being able to start talking about water chemistry, mostly next time, but we'll hint on it today. And as I've mentioned to everyone, there's reading up there in the folder on La Lima. It's from a different book than White. It's called Global Environment. And it's part of chapter 1 and part of chapter 3. You can see they're not very much. This year's only 3 pages. Okay, so water is a super important compound. I think we all know that. It interacts with all the other spheres. So it's what makes the hydrosphere so pervasive in geochemical flows on the surface of the planet. It's the way in which it interacts with the geospheres we've just been talking about with soils, the way it interacts with the atmosphere, the way it interacts with organisms, and the way it interacts with humans. And exogenic, remember that term, just means the surface of the earth. Water cycle transports a huge amount of chemicals, both essential chemicals and hazardous chemicals, within the various reservoirs of the natural spheres and in and out of the amphisphere. So we kind of want to understand something about it. And part of the reason water is so important, of course, is that it's a really good solvent and it can dissolve chemicals. But the other has to do with the fact that it moves around, right? It evaporates, it precipitates, it flows. And this reflects largely heat transport, density-driven flow that involves heat. And we'll talk a little bit about that. And in addition to transferring between reservoirs, like water evaporating out of a lake or into the atmosphere, water, if a body of water is big enough, it can get variations in its physical properties from is it hot, is it cold, is it salty, is it fresh, etc., that are largely driven by heat, which can set up thermal gradients within the body of water, which cause some of them to convect. Think about the oceans. It causes some of them to stratify. We'll talk about that a little bit more, but those are things like lakes. And that can cause enhancement or changes in the chemical properties of those sub-reservoirs. And so we want to think a little bit about that aspect as well. So these are a couple of tables. They're based on the same data. They're from two different textbooks. One of them from the book that you're going to be doing some reading from, and another one from another book that I used to use back about 10, 15 years ago. And I put both tables up here just to simply point out that there's some interpretation around the edges on some of these numbers. They're not, I wouldn't take them as absolutely precise. Like if you look at the volume of the oceans relative, this one here has 97.25%, this one here has 95.96. These things change annually. There's certain assumptions that go into them. You can see that there's two categories of groundwater in this table and one category of groundwater over here. But I just want you to get the gist of the fact that in the exogenic hydrologic cycle, the vast majority of the water is in the oceans, 96 to 97%. The next biggest thing are ice sheets and glaciers, right? These are obviously under pressure right now due to anthropogenic global warming, but that's a significant fraction of the fresh water. It's the biggest material besides the ocean in the hydrologic cycle, exogenic hydrologic cycle. So this is really where most of the fresh water on the planet is. And then beyond that, we get to groundwater reservoirs, which the reason it's useful to separate deep and shallow is that deep is stuff that we normally too deep to get for kind of normal, typical human use well water, for instance, supplying cities. And again, depending on how you parse this out, you know, it's something like 0.2% to 1%. It's small. It's smaller than ice sheets and glaciers. And then we go down from there, right? Lakes are a really small percentage, regardless of which table you look at. We have, you know, soil moisture, rivers, etc. These are all tiny, tiny fractions of a percent, which illustrates that they're precious resources, but also, especially, we can think about the distinction between some of these are just kind of sitting there and some of these things are moving, like rivers. Rivers transport a lot of dissolved chemical through the rock cycle and various other interactions with the biosphere, for instance, even though they're really small volume, right? So they represent a high flux part of the hydrologic cycle, even if they aren't volumetrically important. So we want to think about things from two perspectives. How big is a reservoir and how much is the reservoir moving, and what is it, how does it move, what does it interact with, how is that movement vary seasonally or regionally, you know, by geographical parameters, etc. So that's just highlighting the oceans. So there's this other feature, and we looked at this phase diagram before. I just want to remind you of it, that we find all three forms of water, you know, in vapor, in liquid, and as ice at the surface of the Earth. Is a part of what makes our planet sort of in a Goldilocks setting, you know, and able to support biological life is the development of a hydrologic cycle that wouldn't be possible if we didn't have all these forms. Okay? And this allows us to have reserves and transfer between reservoirs and seasonality. The water vapor in our atmosphere also does a large control on sort of stabilizing climate on the planet, heat absorption through the greenhouse of our atmosphere. It's a necessary and required aspect of sort of planetary surfaces, as far as we know, to support life the way we know it here on Earth, to have a fully functioning hydrologic cycle, which is dependent on that phase. So here's some other properties of water. These are the properties, and these are the effects. And again, I'm not going to read through the whole thing, but stuff like it's a good solvent. It's got a high dielectric constant, which is good for dissolving ionic solutes. It's got strong, high surface tension, which goes into how it forms droplets and flows and migrates through the ground and groundwater. And so it's an important factor. It also plays a role in physiology and biological systems. It can transmit light, obviously important for supporting photosynthesis. This one's a little bit important. We're going to talk about it. It's highest density in pure water. Now, not salt water, but pure water is at 4 degrees C. So in many materials, as they get cooler and cooler, they continue to densify until they go through a phase change. We all know that the phase change for water between at 1 bar pressure between liquid and solid is at 0 degrees C. And so what this is telling us is that as we start to cool something down, and it gets denser and denser as we cool down to 4 degrees C. And if we continue to cool, 3 degrees C, 2 degrees C, 1 degree C, it gets less dense. That's why ice floats. It's less dense than the water beneath it at basically the same temperature. And again, that's kind of an important property. You can imagine if lakes froze from the bottom up, we would have very different manifestations on the biological systems in that lake in temperate regions that freeze every year rather than freezing from the top down. And oftentimes once they start to freeze, the water beneath it stays insulated and doesn't get any colder. These are some other features about it: heat of evaporation, latent heat of fusion, and heat capacity, which kind of drive exchanges within the hydrologic cycle, especially the evaporation precipitation cycle, and are collectively important for helping kind of set the way in which water is able to transport through the hydrologic cycle. So this diagram here has the same numbers as on this table here, plus minus again with a little bit of uncertainty. And this one's from the burner place that I have you do the reading. And it shows us some fluxes, which we've thought about a little bit already this semester, but I just want to remind you that we can think about the transfer between reservoirs, which are the reservoir volumes are shown with parentheses here. And they're all in units of 10 to the 6 cubic kilometers for the volume, or for fluxes, which are shown here next to arrows, 10 to the 6 cubic kilometers per year. So you think about that, that's like 1 million cubic kilometers. It's a huge volume, right? It's also written out here as 10 to the 18th kilograms per year. I don't even know what name would give something with 10 to the 18th, but it's big. And so throughout all of this, again, you can see second biggest thing, first biggest thing, and in this flux diagram, we can see that more water evaporates from the oceans and rains back to the ocean. There's a slight imbalance here. So that means that we have a net transport of water from the oceans through the atmosphere to the land. Over land, we have some evaporation and precipitation. And again, there's more precipitation and evaporation. And so the balance between those is described as runoff, which is basically going from the continents to the oceans. And if we were to add up all these fluxes, we'd see that they are exactly balanced. And again, these fluxes vary throughout the year. They may have varied over the last several decades since this diagram was made because of climate change. So just take them as a kind of a first order indication of the way in which things work and the kind of driving of hydrologic cycle. And these reservoirs here, like lakes and rivers and groundwater, which hold water, they don't hold very much, but they do. They kind of are part of the flow of material. And so some of the runoff into the oceans is on the surface. Some of it is as discharge directly from groundwater into the oceans. We call that submarine groundwater discharge. That's all kind of subsumed in this calculation that of kind of a transfer function of water from the land to the ocean. So this is just another way to look at that same exact diagram, but just to remind you that we have reservoirs, fixed identifiable places in a system, in this case the hydrologic system, that we can describe as holding. They're a container of material that has a volume or a mass or a molar quantity, however we want to define our reservoir size. And it's got fluxes, which are the transfer of chemicals between them. So I've written just those same numbers again as reservoirs and fluxes. Obviously, these boxes are not to scale. And as we talked about in the first week with reservoirs, sometimes it's convenient for us to divide it up, right? Like we might say the Pacific Ocean, the Indian Ocean, the Southern Ocean, the Atlantic Ocean. Other times we want to think about them all together, just like here. Sometimes we want to think about individual rivers. Sometimes we want to think about all rivers. So we can write these diagrams differently. The more we divide these reservoirs up into smaller parts, lower atmosphere, upper atmosphere, for instance, the more arrows we have to add, the more uncertainty, right? But sometimes we need to have that level of granularity in our interpretation to understand why a system is changing or why a system is the way it is. So in this context, I divide up basically the hydrologic cycle into three kinds of reservoirs. Okay, we've got the stuff that's, well, we've got gas phase water. This is primarily in the atmosphere. Although we can also find liquid water in the atmosphere as well as droplets. We can find solid water in the atmosphere as snowflakes or as small crystals that form nuclei in clouds. Then within the surface water, we've got oceans and lakes, that I've shown in a different color here, because these are big bodies of water that I call them kind of holding tanks, in the sense that they hold water in them. And then we've got all the things that flow. Okay, some of them flow on the surface, some of them flow beneath the surface, some of them flow slowly, like glaciers. But in all these cases, there's a relatively small volume, but there's motion. So we have high flux here. Here we have less flux, big volume, but not so much moving around of stuff. Here, again, small volume, high flux. So this is another diagram of how the world's water cycle kind of looks, and slightly different units on here than the previous tables I've shown you, but the arrows are meant to be scaled relative to the kind of size of the flux, right? So here's again that big flux of evaporation precipitation over the oceans and evaporation and precipitation over land. Well, evaporation and precipitation over land. And instead of just showing you one arrow, which the last flux diagram gave you the net, this is showing you like a balance. Well, how much water falls to Earth by precipitation and comes back out through evapotranspiration, how much falls out into bodies of water by precipitation and comes back out by evaporation, etc. How much is in the ground. But the numbers are basically the same in the, as prior, but you can start to think about the way in which this process fundamentally controls a bunch of stuff on the planet. It controls the development and maintenance of ecosystems. It controls the rate at which rock is broken down and transported and weathered in the rock cycle. It controls the supply of chemical nutrients into the coastal ocean, which supports ecosystems that humans depend on for food, fish, and coastal resiliency, and the list goes on and on. So there are a lot of ways in which this cycle is fundamentally important. So when we talk about motions, right, and sizes and transfers of chemicals, we use the term reservoirs, which we've talked about before, fluxes, and there's something called transport equations, which we'll get to a little bit later in the semester, which allows us to quantify these very precisely in space and time. But I just want you to, to remember that there's a purpose to this way of thinking about things, which is to help us conceptualize and quantify the relative rates and sizes of, whatever you want to call them, for lack of a better word, reservoirs that are holding chemicals that are transferring between them on Earth, okay? And one important thing is this residence time idea. Residence time is the mean time that something spends in a reservoir, okay? It could be, the residence time of people in rooms in this building, right, on average. How long do you spend in a particular room during the day? Not every person in this class is going to spend the same amount of time in this particular room today. So it's an average across all the particles. Now you can do it for something like all the water molecules in the ocean, or all the water molecules in the atmosphere, or you could do it for all the sodium ions dissolved in the water in the oceans, right? So it can either be the thing that makes up the reservoir or something that's dissolved into the reservoir or a part of the reservoir. Either way, the way we define residence time is to look at the size of the reservoir, and that could be in volume units, it could be in mass units, it could be in mole units, and the rate at which stuff comes in or out, the flux, which is just a rate of change of the parameter A, again being volume or weight or mass or moles over time. If you think about, we've been talking about the hydrologic cycle, how many, 10 to the 6 cubic kilometers of water in different reservoirs. There were arrows, which told us the flux of 10 to the 6 cubic kilometers per year. That flux is this term, which is a rate of change per time. So when you're writing out a residence time, obviously you want to use the same units for A in both cases. If you're using mass units, use mass in both places. If you're using moles, use moles in both cases. Otherwise, you'll get a goofy answer. So A is the material, and this term, sometimes residence time is shown with the letter T for tau. Sometimes it's just shown as a capital T with a little res under it, which just stands for residence time. Usually people will define it at least once in their text, whatever symbol they're using. And it brings up the next idea, which is what we call steady state. At steady state, a reservoir size isn't changing. If it's not changing, that means the fluxes in and out are balanced. And officially, when you calculate residence time, you should only calculate it for a reservoir that is at steady state, so that it doesn't matter if we use the flux in or out. We can use either, and we'll get the same answer. There are very few natural reservoirs at steady state, right? Just think about, whether we're talking about annual cycles in snowpack in the mountains or the sort of 125,000 year cycle of ice ages, and addition and subtraction of water to glaciers, whether we're talking about the sea level changes associated with that. All of those reservoirs are changing size, right? And for them to change size, it implies that the flux in or out are different. They're not balanced. That's how they change in size. We still calculate residence times for them, and we'll get a different number depending on if we can measure the flux of, for instance, water into glaciers versus water out. We're going to get a different residence time. But both of them will give us an idea, at least the order of magnitude of the average time that, in that example, water molecules spend in that particular environment. And as you'll see, when we start to talk about residence times, you'll see conditions where things will spend days, other places where things will spend years, centuries, millennia, et cetera, on the very vastly different time scales. And the key aspect of this that's so important geochemically is that the longer water, for instance, tends to spend in a reservoir, the more its chemistry starts to reflect that place. And it can develop chemical transformations within the body of water, and stratification and variations with depth and all these other things that are enhanced by longer residence time.
Yeah, if we were to use, if we were to find the residence time, would you be given the flux? Or I know that there's a lot of different equations depending on what you're referring to.
Yeah, it depends. Sometimes you're just given the residence time.
Yeah.
And just like, here it is, blah, blah, blah. And I have some examples coming up that are like that. And sometimes they'll tell you what goes into, there's a lot of kind of nitty gritty, dirty details that go into this.
Yeah.
Imprecisions and estimates and all that kind of stuff. And so it just depends.
Yeah, okay. Because I was just kind of curious, because I know if we were to use it in a homework assignment, if it would depend depending on, I guess, the reservoir, how would the flux be measured, using different equations?
Yeah, well, so I have an example coming up that might illuminate that, but it depends totally on the reservoir.
Yeah.
And how big it is, the conditions of it, and how precisely. So oftentimes people will take advantage of this. Sometimes it's easier to measure fluxes in and fluxes out. Think about a rain gauge. It's easier to measure rain than rates of evaporation.
Yeah. Oh, okay.
So it's oftentimes, and again, it depends on the reservoir, but for superficial reservoirs, it's easier to measure fluxes in when they're coming out of the sky.
Yeah.
But if you're a lake and you're looking at groundwater that's coming in, that's kind of a hard thing to measure. So, like I say, in the nitty gritty details, there'll be some estimates made and approximations to try and kind of come up with numbers.
I see.
So this is an example of a lake, and this lake has a volume, and I put all of these these numbers are all in sort of billions of liters or millions of liters per year in terms of transfer functions. This is a lake. It's got 1,000 units of water in it, and it's got these fluxes coming in and out. And this is an example of did someone go out and measure each one of these things, or are some of them estimated by knowing some of them and then seeing that the lake volume, for instance, does or doesn't change? If it doesn't change and it's at steady state, then you can write a balance equation. If the flux is in, have to equal the flux is out, and you can start to parse them out. But so, for instance, you got 10 million of these liters in these units per year coming in, and 30 coming out. In this kind of hypothetical example that I've set up, you got 50 coming in through river input into the lake, and you've got 20 going out and 10 going out through groundwater flow. This is pretty easy to measure through looking at flow rate within the river. This is pretty easy to measure. This is pretty easy to measure. Difficult to measure, difficult to measure. So in this particular example, it would be easier to measure inputs. These are things that we can gauge and get pretty accurately, and harder to measure outputs. So we can add those up, the inputs and the outputs. And this is a contrived example that I made to be balanced, right? So the total input in and the total output out are the same, which means that the volume of the lake isn't changing. It's at steady state. Like I say, I built it that way. But if we added it up so that this number was higher than this number, then the lake would be growing in size. And if it turned out that this number was higher than this number, then the lake would be shrinking. So we can also say, well, what is the residence time of water in that particular lake, right? So we take the volume and we divide it by the flux, that either the net flux in or out, which in this example happens to be equal, and we come up with 17. That tells us that on average, water in that lake is 17 years old. It doesn't mean the lake's going to come or go in 17 years, and there's always water coming and going. We see that every year. But as a fraction of the total, on average, a molecule of water can expect to spend a couple of decades in there. That gives us some idea about what we call the turnover time for that reservoir. And it's kind of a useful indicator, for instance, well, how long would it take to flush a chemical contaminant out of that lake if it got added into it? We know it wouldn't be centuries, it might be decades. Or let's say we had a severe drought one year and a municipality drained that lake to use it for drinking water. How long would it take to replenish water levels? And again, it depends on what else is happening with the fluxes in and out. But it gives us, it's part of the way we think about reservoirs. So this is a table showing you estimated residence times of different water resources that humans depend on, and the hydrologic cycle is dependent on. And so, water that's in the biosphere spends about a week. Water that's in the atmosphere, maybe 1.5 weeks. Water in river channels, a couple weeks. Water in swamps, 1 to 10 years. Lakes and reservoirs, typically 10 years. This is not things like, Lake Erie or Lake Michigan, big Great Lakes, but it's, typical size lakes. Water that spends time in soils, a couple of weeks to a year. So these are all, pretty short and rapid on a human time scale. Then all of a sudden we get to these categories: ice caps and glaciers, millennia, oceans and seas, several thousand years, and groundwater can be anywhere from, weeks up to 10,000 of years. So in fact, the oldest water that we find, and in this case, we kind of define the age of water as, when was it last in contact with the atmosphere? When did it have the ability to exchange some oxygen, for instance? The oldest water we find is in deep groundwater. It's been isolated from the atmosphere for a long time. And over that time period, it's developed chemical attributes of being isolated from the atmosphere for a long time. In the oceans, as we'll see later today, they have a pattern of circulation, and the deepest water masses in part of the ocean, in fact, here up in the North Pacific where we live, is the water masses that have been isolated from the atmosphere the longest. It's generally not thought to be 4,000 years. It's generally thought to be something more like 1,500 to 2,000. Nevertheless, you can find little pockets in isolated places where it can be older, and it's still of a millennial scale. So along with that residence time comes the chemistry aspect. Okay, and what we find when we look at sort of three aspects of the hydrologic cycle that are pretty easy to define what we mean by rain, rivers on average, and freshwater lakes, is the relative residence time and the total dissolved solids, which we defined a couple of weeks ago, going up as the residence time goes up, right? The amount of stuff that's in a reservoir in the hydrologic cycle is directly linked to how long water spends there. So rain has low TDS and lakes have the highest TDS here, right? The oceans, which we've talked about before, which have much, much higher TDS and water spends much longer there, could also be on this table. I just didn't have any more space. And what is in that TDS, as we've also talked about before, depends a lot on the particulars of the environment, right? It reflects inputs of particles from the local rock, the local biosphere, and those are going to vary from place to place, right? And as a body of water interacts with those materials, they're going to develop different flavors of chemistry that are reflected in the total dissolved solids, even if they kind of come up with roughly the same total dissolved solids from place to place. What's in those solids might vary. So these next few slides, I'm going to go through a little bit quickly, but I just want to remind you that many reservoirs move in the hydrologic cycle, and they move primarily because of heat. And most of the heat that comes onto the surface of the earth and drives the exogenic cycles comes from the sun. Something like 99.98%. There's a little small amount of heat that comes from internal tides, in the Earth-Moon interaction, and there's a small amount of heat that comes from radioactivity. But today, on the modern Earth, in the hydrologic cycle, most of it's driven by the sun, and so all of a sudden you can think about daily changes as we go from night to day. You can think about seasonal changes depending on what latitude we're at and so forth, and the length of day, and all these kinds of things that are driving variations in the rate of motions, which we're defining as fluxes for this discussion, throughout the year in the hydrologic cycle. And when we say here's the flux of water out of the oceans, that's annualized, right? But if we were in a high latitude, the balance between evaporation and precipitation is going to change as we go through the seasons, for instance. Okay. Now, another kind of critical factor about this is that surface bodies of water are heated from above. So everyone knows you go into the ocean, you go swimming, it's generally warmest right up to the surface. And as you go down, it gets cooler. The atmosphere is heated mostly from below, right? Which means that this is the lower atmosphere, the troposphere that we live in. Obviously, the outer atmosphere is directly heated by solar radiation, but much of the light that comes to us from the sun, the atmosphere is transparent to. It hits the surface of the earth, it reflects off the surface of the earth in a longer wavelength, and that is what's absorbed by the atmosphere. So it's mostly the atmosphere is behaving kind of like a pot on your stove. It's being heated from below, from this reflection of the infrared radiation coming off the surface back up into the atmosphere. And so that kind of sets up some thermal gradients. We find the warmest atmosphere, again, I'm not talking about the extreme outer parts of the atmosphere, but within the sort of troposphere and stratosphere, which is the bottom two layer system, the only ones we really interact with, the temperature is basically warmest right near the surface. And in bodies of water, again, the temperature is usually warmest near the surface, but then, that's interesting. Let's see what's going on. Let me just check if I'm, yeah, now I'm plugged in. Okay. Okay, so this is a diagram showing you, illustrating that effect that I was talking about with light coming in onto the planet, right? So for some balance of 100 units of incoming solar irradiance in the visible and infrared wavelengths, some fraction of it gets down to the surface and is reflected back out. Some fraction is reflected out by clouds. some is backscattered by air. This we call our albedo. This is like, if you were flying around in a spaceship and looking at a planet from the outside in the visible wavelengths, what would you see coming back off? And it's part of our heat balance. There's also this so-called long wave, which is just infrared radiation. A significant fraction of the light that interacts with the surface of the Earth is transferred from shorter to longer wavelengths and then reflects back out into space in these infrared wavelengths. We can't see them visually, but they're there. The main difference is that the atmosphere is largely transparent to these, but the atmosphere absorbs this. This is the whole concept of the planet being a greenhouse. If it weren't for the water vapor in the atmosphere, which helps absorb some of this infrared radiation on its way back out, and radiates it back down to Earth or uses it to evaporate and precipitate water and do various functions, the planet wouldn't be nearly as kind of comfortable as it is. And we have much bigger temperature variations from equator to pole and seasonally. And we only need to look at the moon to see those variations. What's interesting about anthropogenic global warming is that, relatively small sense, compared to the total ability of the atmosphere to absorb infrared radiation. We're tweaking it by adding a little bit of extra carbon dioxide. It's wreaking havoc, but it's a relatively small fraction. It basically kind of illustrates the, even though these systems seem to be persistent and long-lived, and we've had, billions of years of hydrologic cycle and relative stability thereof on the planet, that there are things that can happen that can tweak the balance and make it very different in terms of sustainability of life and the way in which fluxes move within the hydrologic cycle and the way in which ecosystems can depend on it. So there's also some things that we call feedbacks. So for instance, we get low albedo, again, surface reflection in the visible wavelength from liquid water and from forested regions. And we get higher albedo from solid water, which means ice, in desert regions. So you can imagine a scenario when we're going into a cooling planet, such as during entering into an ice age, where water is going from liquid to solid, and the planet starts to reflect more light back out into space, bypassing this process of retention of infrared wavelengths, which leads to cooling. So cooling leads to cooling. We call that a positive feedback. You can also find negative feedbacks. Like for instance, when we warm the planet, which puts more water vapor into the atmosphere, which makes it able to absorb more infrared light, we also make more clouds, and clouds contribute to albedo. So we may make the atmosphere better at absorbing infrared radiation, but we also make it better at reflecting visible radiation. So that's what's called a negative feedback. And through some combination of positive and negative feedbacks and some period of time associated with the rates of transfer, the fluxes of water in and out of this, and the rates at which this incoming radiation varies over time, whether it's annually or diurnally or over longer time periods, they all reflect these balances that give us, variations in temperature conditions and heat content, which drives flow. Okay, and this is just a slide sort of showing you these other sources of heat. Most of, like I say, the heat that's available to drive hydrologic motions comes from the sun. This is just an image kind of saying, well, why does the atmosphere absorb in the infrared? And it all comes down to bond motions. So these are a couple of molecules, triatomic molecules, water and oxygen. And in quantum mechanics, one of the ways that chemical bonds are modeled is as springs with a spring constant. And the vibrational nodes of these molecules, which can be, for instance, the spring getting bigger and smaller. It can also be the spring of this angle here changing, kind of going in and out. And there's various other vibrational modes too. They get excited in the infrared wavelengths. So these molecules can absorb in the infrared, hold extra energy in the molecule, which leads to more bond vibration, and then eventually, usually through collisions with each other, they liberate that heat back out again. And that's the basis of kind of, the arrows in and out here of the gases that basically transfer heat from one place to another. It turns out diatomic molecules, which is mostly what our atmosphere is made of, N2, O2, they don't do this. They don't absorb in the infrared substantially. And of course, argon gas, which is a monatomic species, which is the third most abundant chemical atmosphere, doesn't do that. But things like water, oxygen, another greenhouse gas we talk about a lot is methane. That's got more, it's not a triatomic anymore, it's got 5 atoms in it, but it can also be excited in the infrared, as can chlorofluorocarbons and various other things that humans put in the atmosphere. We'll talk about that a little bit later. And this slide just kind of summarizes a couple of feedbacks. The feedbacks I just already mentioned, positive and negative feedback loops between what happens when the planet heats or cools and the kind of response of the atmosphere system to it in a way that retains heat or doesn't. And we'll talk about climate in a few weeks, but for now, I just want you to think about it. It's really the heat content, and especially for water, evaporation, precipitation. That's one thing that's very important, but also the absorption or release of heat, which leads to changes in the density of the body of water that really drive how the hydrologic cycle works. Right? It's just heat. It's just heat. So, for most bodies of water, the primary thing that sets the density is heat. Composition is a secondary phenomenon. In the oceans, which are the highest TDS material reservoir in our hydrologic cycle, composition plays a significant role, but it's still, in my opinion, secondary to heat content in terms of setting the kind of density. And again, remember that when we have a body of water that is heated from above, that means the warmest water is at the top, warm water is less dense than cold water, it tends to float, it's going to stay up there, right? That leads to something called stratification. Warmer, less dense water above cooler, more dense water has an impediment to mix. You can have some winds come in and whip it up, or you can have a roaring river come running in and help churn things up and try to reverse that trend, but it's difficult. Whereas in the atmosphere, because it's heated from below, because of the surface of the Earth reflection, we have a lot of churning in the atmosphere, right? Just think about, like, again, a pot on the stove. You put some water in there and you start heating it from the heating element below. The hottest water is going to be right there at the base, and it's going to tend to rise and circulate because of kind of thermal density contrast. So when we look at the atmosphere, it being heated from below, coupled with the circulation of the planet, gives us these zones of places where, in some places, for instance, near the equator, hot air is rising up in the atmosphere because they're heated near the surface. We also happen to have places where, after water vapor and atmosphere that contains it rises up, at some point it cools and the water vapor condenses and comes out, and that water becomes, that atmosphere changes in density. It also cools and it can sink back to the planet. And so we have these kind of circulation cells in the atmosphere. Over the oceans, they're a little more simple than they are over land because there's interaction with land surface, for instance. But that, coupled with the spinning of the planet, sets up these kind of typical patterns of winds. For instance, we all know we're in a trade wind belt here, which basically means winds coming from the northeast towards the equator. And if we were in the southern hemisphere, it'd be coming from the southeast. And again, this is a combination of this kind of evaporation and rising driven kind of cell of atmosphere right at the equator, and the rotation of the planet. And the reason these wind directions, and when we go off into more temperate latitudes, the wind directions change. The reason these are important is because they set up motions in bodies of water like the oceans, which we'll see in a moment. This is just a little bit more description of kind of what happens as air masses rise and as they sink. and the relationship between evaporation and precipitation and rain belts. We have places where air masses are rising from the surface of the earth up into the atmosphere and cooling. Beneath them, we tend to have more rain. And where these air masses, after they've lost their rain and they're dry, they eventually densify by cooling and sink back down, but they tend to be dry. And so those give us kind of deserty zones. And so when you think back to the kind of global view, we have zones that are wetter and zones that are drier on the planet. So most of the great deserts on the planet are there because of this process. There are some other things that can control why we do or don't have deserts, such as rain shadows from things like large mountain ranges. But there are zones on the planet that are wetter, so here and then up here near the poles, and zones that are drier. And again, it affects not only the sort of surface motions in the hydrologic cycle, but also things like the total dissolved solids. Because if you're in a setting where water is evaporating versus the zone where you're getting excess precipitation, the surface water is going to be more salty and less salty in those two conditions. So these are the currents in the surface oceans. These lighter gray things are the continents. And you can see that unlike the atmospheric winds, which are pretty much circumglobal, the oceans have these pesky continents in the way, right? So while we do have northeasterly trades, for instance, where Hawaii is, which is right here, and we see currents kind of mimicking them, right? This is in the surface ocean, the winds are blowing the currents along, they're driving in, that direction. When the water masses bump up against a continent, they have to turn and change their directionality. This leads to something called gyroscopic flow, which are these circular patterns in each of the major ocean basins. So in the northern hemisphere, the gyroscopic flow is clockwise, and then the southern hemisphere is counterclockwise. And again, these patterns derive directly from these wind patterns. You can kind of compare those two and see it. There's a bunch of other cool things that we'll talk about later that happen when these currents in the surface interact with coastlines or interact with each other, which for instance can cause upwelling from below, which brings water of a very different composition up into the photic zone and can largely affect biological activity in those environments. But to a first order, this basically not only does it set up internal motions in the surface of the body of water, it also gives us the ability to transport heat from the equator up into the Arctic regions, right? Which again makes the high latitude regions of the planet less cold than they would be if we didn't have oceans, right? Because the oceans have these northerly currents that happen on, we call them western boundary currents, because they always happen on the western sides of ocean, that transport heat up. And just think about the Gulf Stream as a common example of that. Okay, so within the holding tank reservoirs, we can separate out the freshwater bodies and the saltwater bodies. The freshwater bodies having their density set only by temperature, and the saltwater bodies having their density set by some combination of temperature and composition. In bodies of water that sit around long enough, they almost always stratify with less dense water on the top, more dense water on the bottom. Oftentimes we will find a very simple layered system where we've got a surface layer, okay, and a deep layer, and a transition zone between them. The transition zone is called the penocline, which is basically where the density change per depth changes very rapidly between a surface zone where the density isn't changing very much with depth and a deeper zone where it's not changing very much with depth. And we find associated with that, for instance, a thermocline where the temperature starts to change very rapidly. I have a plot of this in a second, you'll see it, but we can see that the way heat is absorbed into these bodies of water can then affect whether or not that part of that body of water can exchange with the atmosphere, right? In a stratified body of water, the upper mixed layer can freely exchange with the atmosphere, but everything below that that's stuck in this deep layer can't. This down is below these transition zones that basically have developed to prevent water from the deeper parts of a stratified body reaching the surface. And so, for instance, when we look at the oceans, now this is a plot going through the Atlantic Ocean from north to south, right? Not up at the North Pole, but at the start of the Arctic Circle, and going down through the equator. So just think about like a line going down through the center of the Atlantic Ocean. And then this is like a slice of ocean from the surface. This only goes to 1,500 meters water depth, right? The average depth of the world's oceans is 4 kilometers. So this is like, you know, the top, whatever, third-ish. And we find that the stratification exists throughout the oceans, except when we get to very high latitudes, where deep water can exchange with the atmosphere slowly. And this is on a thousands of year cycle. But that through most of the oceans, if we think about from the temperate regions to the equator, is layered. There's an upper layer, which is mixed and different in thickness, depending on what latitude we're at, partly driven by the intensity of storms and winds. We have this transition zone, and we have a deep layer. Okay? And the deep layer is isolated from the atmosphere. So this is an example of stratification. We can tell that this is seawater because of the salinity values, which we mentioned previously a few weeks ago. And it's not very deep, so this is like a continental shelf setting. And this is measurement of several parameters. We've got the salt content in blue and the temperature content in red. Okay, and you can see here that it's relatively constant with depth, and then all of a sudden it shoots down, and then it's constant with depth. And this is stratified. This is the mixed layer or the upper layer with a constant temperature with depth. It's a lot warmer. This is the thermocline, and then this is the deep layer. And we can see that salinity varies in an opposite sense. Okay, it goes from less salty at the surface to more salty at depth. Yeah.
Doesn't fresh water also sit on salt water? Wouldn't that affect
And I'm not exactly sure.
fresh water? Like, for example, if you look at like Greenland, when it's melting, there's basically a pool of fresh water that sits on top of the seawater. Yes, it mixes, but
Yes, yeah, that's true. There are places in the ocean, you can find this like at the mouth of the Amazon too. If you have high discharge of fresh water into a saltwater body, that can affect the stratification and the variation in density from composition. It's kind of like a secondary effect. But yeah, you can also find places in the ocean that receive a lot of rain or have a lot of evaporation that are going to affect the way salt content varies, mostly in the surface. It's hard to affect the deep water. The deep water is kind of sitting there and it's stratified and it's doing its thing. And things that happen at the surface can, kind of magnify or reduce the amount of variation between the surface and depth, and therefore the steepness of the pycnocline or the thermal. But yeah, there are lots of things that can happen that affect that. So we have some names for these layers. Limnologists, which are people who study lakes, are more creative than oceanographers. So in lakes, the surface layer is called the epilimnion, and the bottom layer is called the hypolimnion, and in between is the thermocline. In the oceans, and this was an image from a textbook. I just took it and modified it to make an oceans version. We just call it surface, intermediate, and deep water. We don't have fancy names for it. But again, things that happen in the surface, whether it's stratified or not, that depend on, for instance, light, are photosynthesis. And respiration follows photosynthesis, but the respiration doesn't require the light. So respiration generally happens throughout the body of water. If there's food available, if there's fixed organic carbon, respiring organisms are going to use it. If there's light, we have photosynthesis going on, which will replenish the organic chemistry. But so we see a bigger variation in redox state and chemical conditions in the oceans than we tend to see in many lakes, in part because water spends more time down here. There's a bigger volume of it that's isolated from the ocean surface, so it can't reoxygenate from the atmosphere. it's isolated from light, so there's no photosynthesis, but there's plenty of food particles raining down. So we get to conditions in the deeper ocean where the oxygen content goes low. Now, we also have that condition in lakes, and we'll talk about that, in next week, in essence. And we also have the timescales over which stratification develops and persists, which is longer and shorter. So there are a lot of complicated parameters that interplay with each other. But for now, I just want you to think about timescales, sizes of reservoirs, and the kinds of processes that happen within a body of water, which are driven by, for instance, the availability of light or not, and the relative oxygen content, which reflects some combination of exchange with the atmosphere, photosynthesis, plus respiration in a net sense. So in lakes will stratify. This is a diagram showing the density of water and the maximum densities here, about 4 degrees C. And if it's a real true freshwater lake in a temperate environment where it freezes during the winter time, then you can imagine as you go into the autumn, coming out of the summer, summer is maximally stratified, it's heated from the top, it's warm, it's hot. And as we start to cool, the surface body of the body of water is going to interact with the atmosphere most quickly in exchange, and is going to go down through this curve where it's getting denser and denser and denser, and it can reach a point where the surface water becomes more dense than the water beneath it, which isn't as directly impacted by the atmosphere. Bodies of water are heated from above, and so that water all of a sudden becomes more dense than the water beneath it, and it causes an overturn. Okay, we call that the fall overturn. Now you can also have a condition in the wintertime, and maybe the lake freezes over. Okay, and then so it's somewhere down over here, less dense, ice floats. We come into the spring, it starts to warm up a little bit, and that first water that is produced is a little bit less dense than the water beneath it, which is maybe a little bit warmer and therefore a little bit denser. And so again, we get another overturn. And so in a traditional temperate region lake that freezes, it can have overturning events twice a year. So that this kind of stratification only lasts for a few months, like 3 months, 4 months. Now there are human activities that can greatly impact the kind of the way ecosystems work within lakes, so that even over that relatively short period of time, it can build up concentrations of nutrients in the deep water and the diminishment of oxygen. It's a process we call eutrophication that can lead to a kind of a very nasty setting. And we'll talk about it next week, but it happens relatively quickly. We go into salt water, we don't see this effect anymore. It turns out that these are the same curves now for density versus temperature, and also versus pressure, which because the oceans are a lot deeper, we tend to experience higher pressures at depth, showing you that whereas pure water has this kind of peak in density at 4 degrees C, seawater doesn't. So seawater, because of the added salt content, doesn't have the same kind of overturning characteristics. There are different things that cause the oceans to overturn. And this is just a graphic summarizing what happens in lakes that stratify and turn over. And if you just focus around on the red lines, those are temperature profiles, right? So during stratification, we've got a thermocline and an upper layer and a bottom layer. During overturning times, the temperature's all mixed, so it's constant. Okay, so this upper set of plots is for a ligotrophic lake. So ligotrophic is a term that means nutrient content is low, so there's not much biological activity, very little photosynthesis. Under those conditions, the dissolved oxygen is largely controlled by inorganic things, which means the solubility of oxygen in water. And in the solubility of oxygen, basically is like the inverse in some ways of temperature. So you can see during overturning times, water is constant, but during stratification times, the oxygen content follows the temperature. So when there's no biological activity, meaning not much photosynthesis up here, not much respiration down here, we actually find more oxygen in the bottom waters because they're cooler during the stratification. Saturation stays different. We go into a eutrophic lake, which is one with a lot of biological forcing, a lot of photosynthesis, a lot of respiration. All of a sudden, whereas during the overturning times, we have this condition of mixing, during the stratification times, look at how different, the temperature profiles are exactly the same, but look at how different the oxygen is. And the difference comes from biological forcing of oxygen through photosynthesis and respiration. Photosynthesis up in the surface, respiration in the deep water. During stratification, respiration will consume oxygen, and this is an extreme example which has gone inoxic, meaning oxygen has gone all the way to zero. We can find a whole gradient of conditions between here and here, but the point being that during stratification in a body of water, and we find this in the oceans as well, we tend to see oxygen being consumed at depth because it's not being exchanged with the atmosphere and because we don't have light penetrating far enough down for photosynthesis. So I'm going to leave it here on this slide, and we have the last few slides in here are about stratification in the oceans. We'll pick it up that topic next time. But hopefully this discussion has helped to kind of illustrate the way in which the physical attributes of things and the biological attributes of things combine together along with rates and rates of change to allow conditions to develop in an environment relatively quickly, like just over the course of months. So are there questions about that?